In this section, we're going to look at the component test for a conservative vector field. And we're going to show that not every vector field has a potential. We're going to start with a vector field, namely our spin field. This is the vector field you'd use to model, in some sense, a tornado, or something spinning in circles. And in order to know if this one has a potential, we want to find a potential, we'll start by, let's try and integrate this thing with respect to x. So if I integrate negative y with respect to x, I get a negative yx. Well, if I integrate the x term with respect to y, I get a positive xy. Now, this negative yx, because it has both an x and a y in it, a negative yx should appear over here, but it doesn't. Because there's a positive xy over here, it should appear on the left, but it doesn't. There seems to be a problem. What's the problem? How am I going to find the potential? If I add those together, I get 0, but this is definitely not the gradient of 0. So we're going to find a way to show no potential exists. And the idea is that the vector field, which is Mn, this term ought to equal fx, and this term ought to equal fy if a potential exists. If I recall that f sub xy and f sub yx should be equal if there is such a function. Remember that second partials, you can take the derivative in either order and you'll get the same answer. Well, these things ought to be equal, which is the same thing as writing m sub y, because f sub x should be m, and that ought to equal n sub x. If those are equal, then there is a theorem, if equal, a potential exists, and if they're not equal, then no potential exists. So over here, we're going to take the derivative of m, we're going to take the derivative, this is supposed to be fx, so take its derivative with respect to y, giving me a negative 1. But the derivative of this term, which is supposed to be fy with respect to x, is positive 1, and negative 1 does not equal positive 1, so no potential exists. Not every vector field will have a potential. There's a very similar test if you're dealing with a vector field that has 3 parts. So if your vector field has an m, an n, and a p, then the idea is essentially the same. This is supposed to be fx, this is supposed to be fy, and this is supposed to be fz. So if you calculate f sub x y and f sub x z, then you ought to be able to calculate f sub x y, and these two ought to be the same. You also ought to be able to calculate f sub y z, and that ought to equal f sub zy, and those two ought to be the same, and f sub x z ought to be the same thing as f sub zx, and those ought to be the same. Let's look at that with an example. Let's suppose our vector field is x plus 2y plus 3z, 2x plus 3y plus 4z, and 3x plus 4y plus 5z. This should be f sub x, and this should be f sub y, and this ought to be f sub z if a potential exists. So let's calculate f sub xy. That would be 2. Let's calculate f sub xz. F sub xz should be, or is, 3. This is supposed to be fy, so if I calculate f sub yx, the derivative of this with respect to x, I just get a 2. If I calculate f sub yz, then I just get 4. If I calculate f sub zx, here's f sub z. If I take its derivative with respect to x, I get 3. And f sub zy gives me 4. Now, f sub xy and f sub yx ought to end up being the same, are they? Yep. F sub xz and f sub zx ought to be the same, are they? Yep. And f sub yz and f sub zy ought to be the same, are they? Yep. Because all 3 of those are equal, there is a potential. And how do we find the potential? Remember, integrate this with respect to x, so x squared over 2 plus 2xy plus 3xz. Integrate this with respect to y, giving a 2xy plus 3y squared over 2 plus 4yz. And then integrate this part with respect to z, giving a 3xz plus 4yz plus 5z squared over 2. Now, I add the results and ignore duplicate terms, so the potential ought to be x squared over 2 plus 2xy. That has an x and y, which means it ought to appear there. It does. Plus 3xz, since it's got a z in it, it ought to appear in the z term, and it does. Then the next term I haven't written down is the 3y squared over 2. It just has y, so I need to compare. This one has a 4yz. It's got a z in it as well, so I can cancel it off. Those we've already written, and then plus 5z squared over 2. That right there is an example of one that passes the component test for a potential. So right now we're just going to look at one more example. Let's look at the function. We'll have it be x plus 2y, 3x plus 4y. And we're now going to ask, does this have a potential? Well, here's fx, here's fy, so let's calculate f sub xy, which is 2. This is fy, so let's find f sub yx. We'll just flip the order, and that's 3. 2 does not equal 3, so no potential. And that is essentially the idea of how you find potential.